Hi everyone, hope you had a good weekend. Okay, so we're going to continue with part 2 of the quantitative stoichiometry. Okay, this is where we get into a few applications of, let's call it QS, right? Quantitative stoichiometry, which are really important. All right, so first one, kind of mentioned it a little bit in the last video, is formulas, right? So it turns out that using grams, moles, molecular weight, you can work out the empirical formula of anything, right? Okay, so if you make something new, some exotic new kind of cancer drug or something, you can do some simple math, figure out its empirical formula, and then with a little trick I'll show you, you can easily convert that to the molecular formula. As we saw previously, there's a ratio, typically 2, right, in the examples we saw. So the real molecule maybe weighs twice as much, so there's twice as many as each kind of atom. So we'll see that come into effect when we go from empirical to molecular. So for example here, say we did have dihydrogen dioxide, aka hydrogen peroxide, right? And we did our math, we could work out its empirical formula, which would be HO, and then using a little bit of ratio math, we'd know the mass of the intact molecule from a mass spectrum, for example, right? And we can just kind of ratio it up to see how many times bigger it is and then just change the numbers, okay? So recall then, empirical formula, which we can figure out using this math, is the lowest whole number ratio of atoms in a molecule, right? Okay, so we can figure that out, and later on for actual organic molecules, we'll scale up, all right? So let's just show you how that empirical thing works with a kind of a nice example. So it's a classic, right? So we have 1.271 grams of aluminum, okay, and we kind of essentially burn it with chlorine, okay? So we have the mass of the reactant, and I've got it down here, right, and the mass of the product. Now, remember, we're working out formulas, so we purposely write an unbalanced equation, right? So some aluminum plus some chlorine makes some aluminum chloride of undetermined formula, right? All we're really interested in at this point is the mass of the reactants and mass of products, right? Okay, so determine the empirical formula of the aluminum chloride. Step 1, write the unbalanced equation. Just use atoms essentially, right? So some aluminum plus some chlorine makes some aluminum chloride. And then we just add in the masses of those two things. We start with this, we weigh the aluminum before we burn it in chlorine. We collect the powder, so to speak, the product, and we weigh it, okay? So, conservation of mass law, right? Okay. Mass of reactants equals mass of products, yeah? So real simple, you can find the mass of the chlorine taken up by the aluminum to form this compound just by doing a simple subtraction. So this minus this must equal this, right? And if you do that math, 5.009 grams, okay? So 5.009 grams of chlorine plus 1.271 grams of aluminum combined together to make something that weighs their combined total 6.280 grams of some formula here, right? Fair enough, right? Fair enough. Now, here's the cool part. Because we have the atom types and the masses, we can just figure out how many moles of each atom we have, right? So we need to use the periodic table to do that. So from the periodic table, you know, I'd say molecular weight of aluminum. If I just look in the periodic table, and you can do this, right? 26.98 grams per mole. That's a conversion factor, i.e. 1 mole of aluminum, 26.98 grams. Remember, that's just the box, right? Okay. So use the periodic table as a stockpile of conversion factors. A mole of aluminum weighs 26.98 grams. Look it up real quick. What's chlorine weigh? It's just the atoms, right? 35.45 grams per mole, i.e. 1 mole chlorine equals 35.45 grams, and that's just that box from the periodic table. Fair enough. All right. So move that up. So let's just recap, right? Remember, and here's that little trick I like to kind of remind you of. In the previous part of this video, I showed you that, hey, there's an easy way to convert between grams, molecular weight, and moles using this pyramidal triangle, right? So if you have any of the two, you can always find the third. We've just worked out the masses, so we got our grams. We just figured out molecular weights. So we'll simply, in a second, just find moles, okay? So the goal is to find moles, and empirical formula is the ratio of those moles, okay? So we've got our grams, We got our molecular weights or atomic masses because it's atoms. Okay. Now, let me just move this down a second. So we've got to work out the moles of aluminum, right? We know 1 mole of aluminum is 26.98 grams. So I can write that if I want, right? 1 mole aluminum equals 26.98 grams. And I can use that as a regular conversion, okay? So I'll show you the regular way first, then for chlorine we use that tricky triangle, right? All right. So we had, if we look back on the previous page, 1.271 grams of aluminum. So 1.271 grams of aluminum times aluminum is 26.98 grams is 1 mole. So just like before, right? Just like the first part of the packet. What do we get? 0.04711. Weights to 4 significant figures. That's 4 significant figures. Mole. Okay, fair enough. So we've got the moles of aluminum. Hopefully that looks familiar, right? We've done grams to moles for atoms before. Now, if I use my triangle, right? If you look at it, I took the grams and really divided by molecular weight, right? So grams divided by molecular weight, because times 1 doesn't do anything, right? So just talking numbers, this number times 1 divided by 26, it's just this number divided by this number. It's grams divided by essentially the molecular weight, right? So if we want moles, let's look at our triangle. Moles, yeah, moles is grams divided by molecular weight. So if I just do that, if I just put in 1 point, let's do the chlorine. Okay, let's get the chlorine numbers. Careful, all right, different number. So for chlorine, 5.009 grams, right? So 5.009 grams of Cl. Now you can do it in the regular way like I taught you, right? But if you just divide that by molecular weight, put the units in, molecular weight chlorine, 35.45 grams per mole. Look at those units, they cancel. 1 over moles is moles, right? Hopefully you get 0.1413 moles of chlorine. All right, so that, folks, is the actual ratio of moles to aluminum to moles of chlorine. We knew the mass of aluminum, we knew the mass of chlorine. We can work out the moles of each atom type, all right? Each atom type, okay. All right, now, if you think about it, that ratio, that many aluminums for that many chlorines, is actually an empirical formula, right? It's just not in whole numbers yet. So it's a ratio, but it's not a whole number ratio, yeah? So what I'm going to do in this step right here, I'm going to actually write down those values as what I call a pseudo-empirical formula, right? So it's the right ratio, just not whole numbers yet. Okay, so that's my pseudo-formula, right? Fantastic. Now, of course, we want that to be whole number ratio, right? So if we look at it, this is the correct ratio, but not whole numbers. Now, this is my favorite kind of physics trick, right? If you want to turn any number into the number 1, and one of these is probably going to be a 1, right? Okay. If I want to turn any number to the number 1, what do I do? What's my mathematical operation to do that? Yeah, it's easy, right? You just divide it by itself. So any number divided by itself is 1. Now, if I divide these by one of these numbers, they'll stay in ratio, right? That's what we want. They have to stay in ratio. So if I do the same thing to both numbers, they'll be in ratio still. But if I divide them by the smallest number will turn to the number 1. And because I divide by a small number, that'll be a number bigger than 1, right? So your trick is divide by smallest number, all right? Divide by smallest. Okay, so I'm just going to divide by the smallest number, which is 0.04711, right? So again, we divide out to make the smallest number number 1, divide by the same number, and it stays in ratio, and it'll hopefully pop into something that's an integer greater than 1, right? A whole number. So work it out. Just divide these out. Obviously, that's number 1. What's that? You got it? It's actually an answer you know. I've just asked you to work out the formula of aluminum chloride. Aluminum makes a +3, right? Group 3. Chlorine makes a -1. 3 minus 1s cancel a +3, right? So the empirical formula is an answer you already knew, okay? Just because of the ion charges. This is why we usually do this with organic molecules, because there's no charges, right? So we can easily work out empirical formulas for ions, and that's what we did the whole time in that last packet, okay? So this one, yeah, it was an exercise just to show you it works, okay? And the easiest way to show you it works is to do something simple, right, which we just did. Okay. Now, so again, empirical formulas always for ionic compounds, so that was just showing you the math, right? That makes sense, yeah? So because it's empirical and ionic, it's the same thing, right? Okay. All right. So, moving on. So, for organic molecules, though, you know, things that are two righties, top rights, right? You know, those combustion reactions we saw, those are all molecules, right? So, for molecular materials, oftentimes, in fact, most often, the empirical formula, which you get from this math, is not the same as the real formula. And we'll go back and look at our dihydrogen dioxide versus HO, right? So this is the empirical formula, this is the molecular formula, right? Now, obviously, there's twice as much of every atom in here as in here, so it weighs twice as much. And that's all we're going to do. We're going to compare the masses of the two formulas, molecular and empirical, find out what the multiplier is, and then just apply that to the formula itself, okay? So you'll always get the actual mass of a molecule, its formula weight, so to speak, from a mass spectrometer, right? It's that parent peak, right? So that mass spec will always give you the molecular weight of the molecule, yeah? All right. And then your math, which we've just done an example of, will give you the empirical formula. Their ratio is the size difference, the multiplier, right? Okay. So if we look at H2O2, okay, this is what we'd get from a mass spectrometer. That thing weighs, let's just do kind of round numbers, 34 grams per mole, right? And then if I do HO, which is the empirical, that thing weighs 17 grams per mole, okay? So what factor scale up is that? Well, the ratio is just 34 over 17, which equals a times 2, which makes absolute sense because H2O2 contains twice as many of each type of atom than HO. Okay, so there you go. And that's the math we're going to do. Okay, so we work out the empirical. Maybe it weighs, let's pick a number, 25, nice and easy. Then we look at the actual molecule, weighs 50. Oh, there's twice as many of each kind of atom. Okay, so find the ratio of the molecular formula to the empirical. This tells you how much bigger the real one is. Okay, all right. So here's a classic worked example. You'll do stuff like, if you ever take organic chemistry down the road, you'll do this all the time, okay? So let's give you the classic organic chemistry question, right? Okay, so if you ever, when you take organic chemistry down the road, just come back, look at this as a nice kind of warm-up, all right? So, worked example. So ethylene glycol, so a real molecule, right? Contains 38.7% carbon, 9.7% hydrogen, and 51.6% oxygen. How do we know that? Because what happens is when you work in a chemistry lab, you make a new molecule, right? You want to know its formula. So you send it off for what's called percent composition analysis. You send it to literally a lab in New Jersey, right? All the labs are in New Jersey in a basement, right? And they put your molecule through a mass spectrometer, fair enough, right? And then they can crunch it into atoms, yeah, so they kind of turn up the juice, they turn your molecule into atoms, and then just basically count what fraction of that as a percent comes out the other end, right? Okay, so 38.7% carbon, 9.7 hydrogen, and 51.6 oxygen, okay? From that, you can work out the empirical formula, which I'll show you in a second, all right? Now, also, because it's a mass spectrometer, the intact molecule can be made to fly down that tube, and that's there, right? So that's the molecular weight, right? So that's the intact molecule, 60. So the intact molecule weighs 60. We know the percent composition of the molecule in terms of the weight percentages, if you like, here. Okay, now here's the big trick, right? I can choose to send the nice people in New Jersey any mass sample I want in the mail. Any mass, send them a gram, 2 grams. I'm going to pretend I've just sent them 100 grams, yeah? So if I send them 100 grams through the mail, and it's 38.7% carbon, what mass would that be? It's the same, right? Because I choose 100 grams, it's actually 38.7%, it's 38.7 grams. So just trick number one, we're going to do carbon, hydrogen, oxygen. We're going to say, hey, it's 38.7 grams because of 100 grams, it's the same number, right? Hydrogen, 9.7 grams. And then oxygen, 51.6 grams. You can, add the percentages up. They will add up to 100. Make sure that's true. Okay. Now, Let's look in your periodic table, right? Carbon 12.011 grams is a mole, oxygen 16.00 essentially, right? And then hydrogen 1.01. So you can convert these to their moles. Remember the first step for an empirical formula, find the moles of each atom and then find their ratio. Okay. So I'm going to show you the kind of the shortcut method, right? So 12.011 grams per mole, right? So it's, molecular weight, grams and moles. As long as you show the work and keep the units, it works, right? So this is mathematically legitimate, right? Moles is grams divided by molecular weight, grams over molecular weight, 3.22 moles of carbon. Okay, here I do it like legitimately, like for hydrogen in the normal way. So 1.01 grams from the periodic table is 1 mole, right? So that's the same idea, yeah? And I'm going to get 9.60 moles. Okay, try that last one in the method you prefer, right? How many moles is 51.6 grams of oxygen? All right, 16.00 grams per mole for me. 3.23 moles oxygen. All right, so there they are. That's the actual number of moles of each atom in 100 grams of my mystery molecule, right? Okay, so that's part one done. We got the number of moles of each atom type. So the empirical formula, and feel free to do the same that I'm doing here. I'm going to kind of do it all as a kind of a ongoing kind of process, right? So I'm going to say, hey, carbon, I've got 3.22 moles. This is my pseudo-empirical. Hydrogen, 9.60 moles. And then oxygen, 3.23 moles. Okay, now unlike the last one, which had kind of small numbers, which are kind of hard to kind of look at intuitively, here we have literally a 3, a 9, and a 3, right? Can you see the ratio? Basically, just looking at those numbers. Well, 3 to 9 to 3 for me is 1 to 3 to 1, isn't it, right? Okay, but we've got to prove it, yeah? We can't just write it down. So we've got to prove, we've got to go through the process. The smallest number up here, so divide by the smallest number to get a 1, and then divide the others to keep the ratio. 3.22. 3.22, 3.22. What do I get? C1. Divide that. H3. O1. Now, if it's 0.99 or, 3.01 or something, remember, this is real experimental data. So if it's just real close to an integer, it's really the integer with error, right? So there we go. That's our empirical formula, right? So if I work out the empirical formula weight, what does that thing weigh? Well, it weighs carbon, which is 12, plus 3 times 1.01, which is hydrogen, plus 16, right? Which equals 31 grams per mole, or AMUs per molecule, right? I'll put grams per mole. All right. So fair enough. Our empirical molecule weighs 31, right? But the real molecule weighs 60. So how many times bigger is the real molecule? Therefore, molecular formula weight equals 60 over 31, which is approximately equal to times 2, right? Now remember, if you did that mass spec extra credit, molecules will fragment down the tube, yeah? So particularly with alcohols, one of the hydrogens is easier to move. So, that's not perfect, right? But it's close enough to 2, okay? So if the thing weighs twice as much, the molecular formula is not C1, but C2, not H3, but H6. Move it up, sorry. You didn't see it, so let me go back. So molecular formula was 60, right? So 60 divided by 31, I'm dividing out the real molecule over the empirical formula. It's times 2 bigger, right? So the molecular formula is C, not 1, but 2, not H3, but H6, not O1, but O2. And that's the molecular formula. Okay, maybe I'll make that. So, just to recap, we work out the empirical formula in our method, we get this one, right? And it weighs 31 grams per mole. How many times bigger is the real molecule? Well, the real molecule is 60 AMUs per molecule, or grams per mole. The empirical is 31. What's their ratio? How many times bigger is this one? 2 times bigger. So it's not C1, it's C2, H6, O2. That is the official formula of ethylene glycol. Okay, ethylene glycol. All right. Ethylene glycol, if you're interested, was once used as a sweetener in certain German wines. There's a whole story on that. I won't get into because of time, but yeah, look it up. It's fun. All right. Now, so that's application number 1, right? That's application number 1. All right. What we're going to do now is talk about the primary application of grams, molecular weight, and moles, which is called finding theoretical yield. Okay. In a nutshell, what is theoretical yield? If you do an experiment, say I put 10 grams of something in a test tube with an excess of another reagent, how many grams of product, if everything went perfect, would I make? Yeah. So it's with math calculating what mass of product will I make if I mix these two reactants, right, with their known weights. Okay. So theoretical yield, the amount of products in grams expected, and that's the keyword calculate. So I'm going to show you how to do that calculation right here for any reaction. Okay, so the theoretical is if everything goes perfect, what mass of stuff am I going to make, right? The actual yield, because it never goes perfect, right? The actual yield is what you actually get out in the oven should you do an experiment or something, you're drying your product, right? Okay. So you actually take it out, it's the actual, so you actually weigh it physically on the balance and you get a weighed amount, right? And if you think about it, the measure of how good you are is just their ratio as a percent, so to speak. So say you calculate just easy numbers, you're going to get 100 grams, right? And then you do your experiment, you take it out and you weigh it at the end when it's all done and it's 90 grams. You should have got 100, but you got 90. What's the conversion? Well, it's 90. It's 90%, right? Okay, so that's what percent yield is. Percent yield is really a measure of how good you are. What you got over what you should have got times 100, right? Okay. Now, don't be patting yourself on the back when you do an organic chemistry experiment later if you get 100% yield, because it's not possible. Okay, so you're aiming for 100, but you never get it. In industry, they do like 96, 97% conversions, which is very, very good, right? Okay, but it's never 100. If you think about it, why not? Why would it always be, even though you did it perfect in industry, why would it be like 97% conversion, not 100, right? It's because of transfer. Every time you do an experiment, right, you're transferring stuff from one container to the next, one container to the next, and that process actually leaves stuff behind, right? So be careful there, right? So when you're doing an experiment, the more steps you have, it's going to kind of take maybe 1% off each time or something, and it's going to lower your yield. In industry, they try and design experiments with the least kind of transfer steps as possible. Okay, so that brings it down a little bit. Okay, which we've got to watch out for. Okay, but also sometimes if we did this experiment at school and we did the calcium phosphate experiment, yeah, we make this precipitate calcium phosphate, and then we do the math later and it's like 120% conversion. It's like you got 20% extra for free, right? So sometimes the yield is too high. What's up with that? How can I make an extra free 20%? Alert the media, right? I've just created matter out of thin air. No, obviously you can't exceed 100, but when you do the math, sometimes you do. It all comes back to, we mentioned it, the oven, right? So when you dry something, you're driving off the water because you usually collect as a precipitate, you have to dry it. If it's not fully dried, obviously there's some water left in there, right? So it can be too high on occasion because it's basically wet. Okay, so there are two common errors. You always lose a little bit when you transfer, so you can never get quite to 100. And then sometimes you can actually get quite a big excess over 100 because it's not fully dry. Okay, now if you think about it, if you do a terrible experiment, lots of transfers and it's wet, you can accidentally get 100%, but don't be patting yourself on the back because you did something doubly wrong. That makes sense. Okay, all right. Now, I am at 23 minutes. This next thing takes probably 10 minutes or so, and it's kind of a thing that needs to stand on its own. So I'm just going to kind of stop real quick and come right back. All right, so we're going to do this kind of longer example. Now, I like to teach this in a rather unusual way, right? It's not the same as the book, which is basically a bunch of chain conversions, yeah? Now, to use an analogy, I like to think of this as like the difference between a map and direction. So if someone tells you where to go, turn left at the Walgreens, yeah. If you make a mistake along your journey, you're done, right? But if you've got a map, you can kind of backtrack and see where to go. So maps are always better than directions, yeah. And this method, which is not my invention, it was taught to me years ago when I was a TA in grad school, okay. This method kind of utilizes a kind of a map method. If you learned something else previously, that's fine, go with it, right? I'll do kind of both just to show that they work really just the same. But it allows you to kind of plan your journey easier. Remember, conversions are all about planning journey. So if I can make a little map, it makes my life easier. Okay. Now, to show you this method, which I call slides and ladders, yeah, okay, so it's a slides and ladders method for finding theoretical yield, okay, we're going to do a classic example. We're going to look at propane. Of course, propane was made famous by this guy, right, who you may know, Hank Hill, right? Hank Hill does what?
I provide the people of this community with propane
right.
and propane accessories.
So, first thing we're going to do, read the question, right? So, this is a classic kind of question. Yeah, you're going to come back to this maybe and look at the method, okay, when you need to do this kind of for your first view, okay? So I'm going to take 5 grams of propane, and there's the formula, and I'm going to combust it, right? So we combust an organic, right? So we know what the products are going to be, carbon dioxide and water, yeah? And then the question says, what mass of water is formed? What mass of CO2 is formed? And a little kind of a side trick, we can figure out the volume of CO2, all right? Okay, so we're going to work out the expected mass of products, right? Now, step 1 is a multi-step process, is write a balanced chemical equation, all right? Now, what I'm going to do is kind of do it kind of on a separate piece of paper. So I'll show you the rules and the regulations as we go, but I'll kind of do it on a separate piece of paper. And I'm going to combine step 1 and step 2. If you have the piece of paper in front of you, actually, I'm not going to use the same piece of paper. I'm going to use the piece of paper you have, right? So in front of you, you have this, right? So I'm going to combine step 1 and step 2. Okay, so we'll read this again in a second. I'm going to write my equation here. So propane, C3H8 liquid. Combustion, O2 gas. So step 1, write a balanced chemical equation, right? CO2 gas plus H2O. That temperature, gas. You could write liquid, it'll be okay, but gas, right? Now, we've got to balance this thing, okay? So step 1, write a balanced equation, okay? Okay, we're burning propane. We're burning propane, okay? Burning propane, balanced chemical equation. All right, so there it is. Now let's just balance it up, right? Hopefully we're okay with this. So 3 carbons in the 1 molecule, I need 3 CO2s to get 3 carbons, right? 8 hydrogens, well, they travel in pairs, so I need 4 of those. How many oxygens trapped? 2 3s are 6, plus 4 is 10. I need 5 oxygens. So it wasn't so bad to balance. There we go. All right. Looks familiar, right? If you did that extra credit, it's the same one. All right. Now, here's the big trick, right? We're going to convert between grams, moles, and molecular weight all the time. So up here, kind of have this triangle ready to go because it really allows you to convert quickly and efficiently, right? Okay. Now, in order to use this triangle quickly and efficiently, I'm going to set up what I call a grid, right? And each formula is going to have its own like column, right? Called these ladders. In a second you'll see why. Okay, and then I'm going to have 3 rows, right? So those are my 3 ladders. Sorry, those are my 1, 2, 3, 4 ladders. And then I got 1, 2, 3 rows. It kind of looks like a grid now, doesn't it, right? And I'm going to give these rows titles: grams, molecular weight, and moles. All right. So I've set up a grid system which will allow me to convert and navigate very easily between grams, molecular weight, and moles. Okay, now, step 3, once you've got the balanced equation and you set up your grid, think about where you want to go, right? So the question said, I won't go back and look at it, I'll just paraphrase, right? It's always the same question, right? What are the masses of the products? And they're here, right? So think of each reactant in each product having a line for grams, a line for molecular weight, and a line for moles. That's our destination, grams of product, right? And if you like, you can write TY there for theoretical yield, right? So that's our journey. Yeah, that's our journey, okay, to find these numbers in these boxes, yeah? Okay, you can do a chain, right? So 1, 2, 3 link in the chain conversion for each, or you can follow a map, okay? Now, next thing. Fill out as much information in this grid as possible. Well, we started already. We've got the masses of products, right? Those are called theoretical yields. That's our destination, right? And then we can look back at the question and just see what it says. So let me move this down a little bit. Okay. So when we read the question, let me get on page here. There you go. So when I read this question, It says 5 grams of propane was combusted. 5 grams of propane. So I put 5 grams in the propane column for grams, right? 5 grams of propane. It's combusted in excess oxygen. Now here's a little trick. Whenever you burn something in the air, the oxygen in the air will never run out, right? Because it never runs out, it doesn't affect the math. We'll talk about this in more detail later. It's called excess and limiting reagents. But for now, just write excess, right? So it's not going to affect our math, right? All right. Now, so we've got our top row, the things we want to find, the grams of reactant, and, the excess reactant. Okay, later on when we do this with limiting reactant, put a number there, but for now, we don't need it. Okay, what mass of water, what mass and volume of CO2? So those are those boxes there. Okay, all right. Now, what else can we fill in? Well, look here. We have the formulas for each thing, right? So we can fill in this molecular weight row. Okay, so just for practice, work out these molecular weights, write them in these boxes. Okay, come back when you've done that. Okay, now this is one of those danger Will Robinson things. Okay, the definition of molecular weight is the mass of 1 mole, not 5, not 3, not 4, just 1. So we put down the mass of 1 formula in this box, right? These balancing numbers come in later. Okay, so what's the mass of 3 carbons and 8 hydrogens? 44.11 grams per mole. You probably got that because there's just 1 there, right? If you wrote 5 times 32, whatever that is, that would be incorrect. It's just the mass of 1 molecule. 2/16 are 32. CO2, 3 of them, don't care. It's by definition the mass of 1 mole, 44.01 grams per mole. And water, familiar water, 18. Okay, so hopefully that makes sense, right? Okay, now we filled in all we can. Yeah, we filled in all we can. Got the mass of starting material. It's burnt in excess. We want to go here. Yeah, we got the molecular weights of all these things. Now, a gram does not react with a gram. You're thinking, oh look, 1 reacts with 5. That's true. 1 molecule reacts with 5 molecules, not 1 gram and 5 grams, because they weigh different for a mole, right? Right, different, right? So moles react with moles. So to make this work, we have to turn it into moles first. So our journey is to climb down. This is why it's called slides and ladders. Climb down, slide across, and then climb up. So that's the journey planner, right? And if we did this, and we'll kind of show you with a traditional chain conversion in a minute, it's a 3-link in the chain. Each link is an arrow, right? But this map makes life easier, all right? So let's see what it says. Convert grams to moles by climbing down a ladder. Okay, now look, moles is what? Look at our triangle. Moles is grams divided by molecular weight. So real simple, here's the neat trick. You divide to go down. You divide to go down, right? So grams to moles, grams divided by molecular weight, 0.113. Now here, it doesn't matter, right? Because later on when we do limiting, it'll matter, but that doesn't come into the math, yeah? So 5 grams of propane is 0.113 moles of propane. Fair enough, and that's all we need for now, right? Now, here's the trick, right? Why is it called slides and ladders? Well, you just climb down a ladder, now you're going to slide across, yeah? Look at this. 1 mole of this, sure, it reacts with 5 of these to make 3 of these and 4 of these. That's a ratio. 1 would make 3, right? 1, if it was water, would make 4, right? How about 10? 10 would make how many CO2? 30, right? 10 would make here 40. 100 would make 300. 100 would make 400. It's a ratio, right? So 1 mole or 1 molecule makes 3 moles or 3 molecules, depending macro or micro, yeah? So it's a ratio. I don't know this number yet, but it's easy to figure out, right? So if 1 made 3, 0.1 will make 0.3. With all the change, it's just going to be how many times bigger to go from here to here? It's going to be 3 times bigger, yeah? So that's the trick, yeah? So 1 makes 3, so 0.1 makes 0.3 with all the change. It's 0.113 times 3, right? 0.339. Fair enough. If you understood that one, 1 made 3, so 0.1 essentially made 0.3 with the change, right? What's this one? 1 makes 4, right? So how many moles of water am I going to make from 0.113 of this? If you wrote 0.452, you are correct. Fair enough, right? Okay, now climb down, first leg of the journey, slide across. Now we just climb up to get the answer, right? So it's pretty simple, actually, all right? Hey, if you divide to go down, let me show you. If you divide to go down, what do you think you do to go up? Well, yeah, multiply, right? 1 grams. Grams is molecular weight times moles. Multiply to go up. 0.339 times 44.01, 14.92 grams. And here, 8.15 grams. Okay, now, that's awesome. Okay, that's awesome. Now, if you think about it, conservation of mass, yeah. So this was our destination. Just as the quick aside here, right? If you were curious, well, how many grams of oxygen from the air did we use, right? Well, the products weigh 14 plus. Let's just figure it out, right? What do the products weigh? 14.92 plus 8.15. So the products weigh 23. Let's right here. 23.07. grams on the right, yeah? On the left here, 5 grams plus something is going to be the same mass, right? So 23.07 minus 5 equals, that would have been 18.07 grams. So out of the billions of metric tons of oxygen in the atmosphere, we actually used 18 grams, right? Okay. If you wanted to work it out, you could also work out how many moles that was, right? Okay. And there's a couple of ways you can do that. You can climb down, so grams divided by molecular weight is moles, or just say this, right? One of these reacts with 5 of these. So what is 0.113 times 5? 0.565. That would have been 0.0565 should we have used that number, right? Now, if you think about it, this chart is consistent. I can get this number this way, or I can get it this way. Just do it real quick. What is 18.07 divided by 32? There it is, 0.56, 0.56. Okay. So you can fill out any grid you like in the chart. But it's interesting because later on we'll see we did this for academic purposes. We filled out every single box, right? In the future, when I just want maybe this number, you just plan that journey. You just actually fill out maybe 3 or 4 boxes, yeah? So just fill in what you need for your journey when you kind of do it for real. Okay. All right, now here's a quick thing. So that's 99% of it. Okay. Finding theoretical yields. Finding theoretical yields, awesome. Right, okay. But here's a quick aside. We're going to do gases in much more detail later. All right. Turns out if you have a gas at what's called standard temperature and pressure, so that's 0 degrees C, 1 atmosphere, yeah, the distance between the particles is like the same average number for any gas, yeah. So if I have a 1 mole of gas and I add up all the gaps, essentially, I always get the same volume. So 1 mole of any gas, doesn't matter which one, always takes up the same amount of space under these conditions, and that magic number is 22.4 liters. And that's a conversion factor, right? 1 mole of gas equals 22.4 liters. So I can convert moles to liters for any gas, right? Okay. If I think about that, then, hey, there is no box up here for volume, but because the question wanted the volume of CO2 created, I can take this number on the side, right? And I can say, hey, 0.339 moles CO2 times 1 mole is 22.4 liters equals 7.59 liters, okay? Just an aside calculation. I like to introduce this now because it sets you up for some good success later, okay? You can take this mole number of any gas, convert it to volume, just using the relationship 1 mole is 22.4, okay, liters. All right, so depends on your level of confidence here, right? My advice is have a shot with these, right? Have a shot with these. Now remember, the great thing about the grid is you can navigate to any position, right? Okay, as long as you follow those simple rules from before, you can navigate to any position. You could actually work out, for example, the mass of reactant you need to make something happen, which is this one, okay? All right, then we've got magnesium burning. We saw that one earlier. That was our first ever balanced equation. Don't fall into the old trap, right? Okay. And then there's a kind of a simple one. Okay, we're not going to do the alum lab. We didn't do that this semester. All right, so give it a shot. Come on back and I'll show you how to do it. All right, so first one, calcium carbonate reacts with HCl to make calcium chloride, CO2 and H2O. If they balance it, it's just simple, right? Grams, molecular weight, moles. Now let's set up the grid. Oh, I think my camera just did something weird there. Back to the voice control issue. Okay, so I just mentioned that, hey, we do need to figure out volume of CO2, which we can do from its moles, just like we did on the previous page. Okay, so we've got to fill out everything we can. Right now, I like this question because when you work out the molecular weight of calcium carbonate, it's right on 100 grams per mole, right? So, you know, on the test, use all the sig figs, all right? That's 30, it's just one molecule, 35 plus 1 is 36, 36.45 grams per mole. Calcium chloride we did before for an example, 111 grams per mole. 44, 18. Okay, so I'm doing kind of rounded numbers just for speed. You would use all the sig figs from the table on your test. Okay, so our journey, divide to go down, slide across, climb back up. That's what they want us to figure out, right? We can do it, right? Because one of these reacts with two of these. So whatever this number is, I need twice as much. Okay, so 5 divided by 100. 0, 5, and put the sig figs on there, 0, 0. So, hey, I need twice as much. 1 reacts with 2, so 0.05 needs twice as much, right? 0.100. Fair enough. This is when math's easy. 0.1 times 36, 3.65 grams. Okay. Just for fun, we can fill out the rest of the chart. 1 reacts with 2 to make 1, 1, and 1. So 0.05 needs twice as much. Then it's back to that same number. 0.05. 0.05. 0.05. We can climb up. You can fill these in. Let's just do it real quick. .05 times 111 equals 5.55 grams. 0.05 times 44 equals 2.2. And finally, 0.05 times 18 equals 0.9. Okay, so 5 and 3 is 8, 5, 6, 7, 8. So the mass of the reactions equals the mass of products. It's a consistent chart. Okay, now that quick thing on the side, we've got 0.05 mole of CO2 times 22.4 liters is 1 mole. What do we get there? 1.12 liters. Okay, all right. Now then, hopefully you didn't fall into the legendary trap, right? So we're going to burn magnesium oxide. MgO is, sorry, we're going to burn magnesium to make magnesium oxide. My mistake. Same as before, right? Remember that as a 2, 1, 2 situation when we did that before? Yeah, 2, 1, 2. So grams, molecular weight, moles. 2 magnesium, sorry, let's make the grid. Read the question. What mass of magnesium oxide? So it's a classic theoretical yield question. When 1.56 grams of reactant is directed in air. If it ever says air, it's excess. It doesn't come in with a math, okay? All right. Although we can figure out what volume of oxygen was consumed by taking the moles and turning it to volume, right? Okay. So we have 2 destinations, okay? We go to here and we also go to here. All right. Now, that's what the question gives us. 1.56 grams of magnesium reacts with excess oxygen to make some unknown theoretical yield over here of magnesium oxide, right? So we need the numbers. Magnesium periodic table, 24.3 grams per mole. Oxygen O2, 32 grams per mole. And then magnesium oxide, remember it's just the formula, 24 plus 16, 40.3 grams per mole. Fair enough. Divide to go down. 0.06 0.64 moles of magnesium. Hey, 2 makes 2. That's the same number, right? So what do? I multiply by 1. It's the same number, right? So I make 0.064 moles here. Multiply to go up 2.58 grams. Okay. Interesting. Now you have a choice, right? If you want to figure out the number of moles of oxygen used, you can work out the difference in mass here and just climb down. Or you can say this, hey look, 2 reacts with 1. Careful, right? 2 reacts with 1. It's half as much, so it's half of that. So it's 0.032. All right, so take that on the side. 0.032 moles of O2 times 22.4 liters is 1 mole. What do I get? 0.717 liters. Okay, that's how many liters of air we use in the process. Okay. Sorry, liters of oxygen from the air we used in the process. Okay. Okay, you could have gone this way or this way, it doesn't matter, right? Okay, now, finally, this one here, nice and easy. This is just percent yield equals actual, what you got, over theoretical times 100 for a percent, right? Okay, so what do we get? A student recovers, that's actual, 1.59 grams, when they should have produced 2.32 grams times 100 for a percent equals 3 sig figs, 68.5%. Okay. All right, oh, sorry, move that up. All right, so hopefully all that makes sense. The trick with these is just to practice, all right? Now, I will show you as promised, right? As promised. Maybe I'll kind of do it on the side here. Yeah, if I want to work out, actually I'll do it on a separate piece of paper just to show you. All right. So maybe you're familiar with this from high school or maybe somewhere else, yeah? Remember, each arrow in the process is a link in a conversion factor chain, yeah? So if I want, let's just say, grams of MgO in this second question, right? I'm going to show you how that works. So I'm going to start with 1.56 grams of Mg, all right? And I'm going to go to moles, right? How do I do that? Well, divide to go down. I'm really multiplying by 1 over 24.3. So that's the first link in the journey, right? First step in the journey right there. That's the same thing, right? So that's step 1, all right? Then we have a weird conversion factor. 2 magnesiums react to make 2 MgO. So 2 Mg, we put this weird symbol, is stoichiometrically equivalent to 2 MgOs, right? It's just the 2 makes 2 thing, right? So 2 Mg, 2 MgO, right? Before it wasn't necessarily the same number, right? But it shows you we're just multiplying by 1 essentially to go from here to here, right? So that's that step, this conversion here, right? And then finally, we have to go up, right? So we're carrying, all right? Oh, moles of MgO, moles of Mg. We're carrying moles of MgO, right? Okay. 1 mole MgO is 40.3 grams. We just turn the grams per mole upside down, right? Equals 2.58 grams. I don't mind which way you do it, all right? It has the same exact math. This is just a graphical representation of this, okay? I prefer the map. It's a little bit more work, but it's more easy to follow. If it's the first time you've done this or it's been a while, I say go with the map. If you're a veteran, if you've done this before and you like it, stick with it. I will grade both the same as long as it's got the right math. As you can see, mathematically these are identical, right? So that's okay. All right. Now then, limiting reactant problems. This is where it gets a little interesting, right? So in previous examples, we had an excess reagent which was never going to run out. Okay, when a reagent never runs out, it doesn't affect the math, yeah? But sometimes you have to kind of look at which one runs out to determine how much product you make. That's called a limiting reactant problem. Let's give you something simple to start, right? So let's say I make a sandwich, right? So my balanced chemical equation for making a sandwich is 1 slice of ham plus 2 slices of bread turns into 1 sandwich. That's a balanced equation for making ham sandwiches, correct? Okay, now let's say I hunt through my fridge and I find 4 slices of ham, right? Then I go to the cupboard and I found, wow, we've got a whole loaf of bread in there, right? We've got 24 slices of bread in there, all right? Common sense. How many sandwiches can you make with 2 slices of bread and 1 piece of ham per sandwich when you've got 24 slices of bread and 4 slices of ham? What's your answer? 4 sandwiches, right? 4 sandwiches. Think about that for a second, yeah? So if you think about it, 4 slices of ham, and it's 2 slices per 1 ham, I need 8, right? So if you think about it, that's really 16 plus 8. What I need and what's left, all right? So I have an excess, right? So whenever I have an excess, it never runs out. I can only make 4 sandwiches because I run out of ham. That's called the limiting reactant, okay? So limiting reactant problems are just like regular slides and ladders, but you slide across only with the thing that runs out, okay? So you have to kind of climb down twice, okay, work out the moles of each reactant, and then just look at their ratio. Hey, I'm going to run out first. I'm not. Slide across with the one that runs out. I can only make 4 sandwiches. Doesn't matter if I got the world supply of bread, right? Doesn't matter because I ran out of ham, okay? Okay, so limiting reactant problems, as you just saw with the sandwiches, is pretty straightforward if you just get the concept, okay? Now, this one, instead of ham and bread, think of this like, you know, maybe cheese on toast, right? But this is the cheese and this is the toast. So silver nitrate and sodium chloride react in a 1-to-1 ratio, right? So just like the sandwiches, 1 reacts with 1, 1 reacts with 2 is a ratio, okay? So in a test tube, 1 mole of silver nitrate will react exactly with 1 mole of sodium chloride. However, as we know, it's almost impossible to make that happen, yeah? So just by doing the experiment, as hard as we try, we'll never get exactly 1-to-1. So by definition, there'll be a little bit too much of one, not quite enough of the other. So one will be excess, one will be limiting all the time. Okay. So let's look at this question right here. So if I have 1 mole of, let's look at the question. Sorry, the question. 1 mole of silver nitrate, 1 mole, and 1.5 moles of sodium chloride. Simple questions, right? Which one is there too much of? Which one is there in excess? Well, 1 reacts with 1, but I have 1.5, all right? So there's obviously more of this when in a 1-to-1 ratio, okay? I have to think about the ratio. In the sandwiches, 1 required 2. Here, 1 requires 1. So 1 versus 1.5, obviously 1.5 is excess, right? So that's NaCl, which is limiting, glass half empty, glass half full. If I have 1 of this to be perfect, I would need 1 of this, right? So this is not enough, that's too much, yeah? So you can go this way, 1 needs 1, or you can go the other way, 1.5 needs 1.5. If I start this way, 1.5 needs 1.5. Well, that's not enough, is it? So that's limiting. Okay, so that's AgNO3. Okay. Now, just like the sandwiches, we run out of ham, right? Which one of these do we run out of, right? So 1 reacts with 1 to make 1 and 1 from the stoichiometry. I've got 1 mole in here, and I've got 1.5 moles in here. So this is going to react. 1 mole reacts with 1 mole to make 1 and 1, right? So I'm going to make 1 mole. 1 reacted with 1 from the 1.5. So how many moles of NaCl will be left? 0.5, right? So I like to think of 1.5 as 1 plus 0.5, right? There we go. The 1.5 is 1-to-1 ratio. 1 with 1.5 in a 1-to-1 ratio means 0.5 too much, right? What you use and what's left. I call that the true excess. Okay, so the trick, hopefully, always think about the sandwiches if this, gets a little tricky sometimes. It's all the concept, right? If the concept gets tricky, just think about the sandwiches. You're comparing the ideal ratio from the balanced equation with essentially what's the ratio in the test tube, okay? And then you can figure out from that ratio which is excess, which one's limiting. The limiting reactant will always finish first. You can't make ham sandwiches once you run out of ham, so you slide across in the slides and ladders with the limiting reactant. Okay, so let's take a look at some questions. All right, now maybe we'll do the first one together. That's probably a good idea, right? And then you guys can kind of try the rest. All right, so as I mentioned, we don't really try and put them in the test tube in the right ratio at all. We just throw some stuff in and do the math, right? So in this case, we'll do exactly the same thing. We're going to put 10 grams of each reactant, right? 10 grams of each reactant in each case in a test tube, and then figure out theoretical yield of products, okay? So work out the mass of each product formed, theoretical yield, right? Assuming 10 grams of each reactant. The trick, use regular slides and ladders, but work out the moles of each reactant. Slide across with the one that runs out first, the limiting reactant. So, of course, we have to balance. You know, we never forget our routine. All right, there we go. Now, so it's grams, molecular weight, and moles. Now, if you do this with the traditional method, when you do a conversion chain, you have to do 2 conversion chains and then figure out, like, you know, through comparison, which is the bigger or smaller number, right? So, I don't like to do that. I like to use common sense, right? So, let's call it sandwich logic, right? Okay. So it's my favorite reaction. There it is. So we've got some chalk, some HCl. We're going to make some products, right? So our destination is like a classic. We're going to figure out these, right? And we start in each case with 10 grams, or 10.0 grams, I should say. 10.0 grams. Molecular weights, well, we can just flip back. We can work them out. You know, we've done these before. So that's 100 grams per mole. 36.45 grams per mole, 111 grams per mole, 44 grams per mole, and 18 grams per mole. And again, you know, on the test, full sig figs from the periodic table. Now, this one's nice because it's, you know, 100 divided by 10. Hopefully you got that one. 0.100, 3 sig figs, right? 10 divided by 36.45. 0.27, let me get that last digit. 10 divided by 36.4. All right. 3 sig figs. All right. Now, this is where we have our limiting reaction. So we've climbed down the ladder. Yeah, we climbed down the ladder. And the question is, which one of these will run out first? Which one is the limiting reactant? Once it's run out, you can't make any more product, so that's the one you slide with, right? Now, don't get distracted. Just because it's a bigger number does not mean it's necessarily excess, right? Okay, because it has to be, in this case, twice as big, all right? Now, there it is. 1 reacts with 2. This is what I like to do, right? So watch this. Cover that up, all right? So 1 mole reacts with 2 moles, right? So 0.1 in that ratio to be perfect needs what? 0.2, right? So if the number under my finger is bigger than 0.2, it's excess. If it's smaller than 0.2, it's limiting, right? It has to be 0.2 or bigger because 0.1 reacts with 0.2 to be perfect in a 1-to-2 ratio. Let's look at it. 0.27, right? So that's excess, yeah? It's 0.074 in excess. So that means that one is limiting. Do you see why it's 0.074? Because that's what I need. 0.2 plus 0.074, right? That's the excess, yeah? Now, like I said, just because it's bigger doesn't mean it's excess. If that was, say I had 0.17 under my finger, right? I'd reveal, you know, say 0.17, but it needs to be 0.2 because it's a 1-to-2 ratio. So it'd be actually limiting in that case, right? So be careful. Make sure it's in the right ratio. And the one that's too much in that ratio is excess. The one that's not enough in that ratio is limiting. So we're going to slide across with this one. And this makes life really easy, doesn't it? Okay. 1 reacts with 2 to make 1, 1, and 1, right? So 0.1 reacts with 0.2 from the 0.274 to make how much? 1, 2, 1, 1, 1. We slide over with the limiting reactant. Okay, so it's 0.1 every time. That makes life easy. Then to climb up, hopefully you can do the math without thinking too much about it. There we go. All right. So the trick for slides and ladders, for limiting reactants. Climb down with both reactants if one, if it doesn't state one's excess, you have to figure out which one is essentially, right? So climb down, we figured out this one was excess, it's not going to affect the math. This one runs out, it does determine how much product. I can only make a ham sandwich while I've still got ham, right? I run out of ham, that limits how many sandwiches, okay. All right. Now this one, very similar to the previous question. Grams, molecular weight, and moles. Again, try, it's all balanced 1 to 1. 10.0 grams, 10.0 grams. Destination, destination. Okay. Now, molecular weight, AgN, 3 O's. Good to practice. I get 169.9 grams per mole. 58.45 grams per mole. AgCl 143.4 grams per mole and 85 grams per mole. Okay. Again, divide to go down, figure out the amounts of moles. Now a bit easier. This was like the ham sandwich up here, 1 ham and 2 bread. This is like the cheese on toast, 1 to 1, right? So let's get these moles and figure out the ratio comparison, right? Divide to go down, 0.059. Divide to go down, 1.7. That's just my little trick, right? I'll do this. 1 reacts with 1. 0.059 to be perfect would need 0.059. Is it bigger or smaller than that? It's bigger, so that's excess. That's limiting. Okay, so 0.059 reacts with 0.059 from this larger amount because it reacts in a 1 to 1 ratio to form 1 and 1. 0.059, 0.059. Okay, multiply to go up. 8.5 grams, 5.0 grams. Now, you may be having a bit of an alarm bell in your head, right? Oh look, mass of reactants is 20 grams, 10 plus 10. Mass of products is 8.5 and 5, right? So that's only 13.5. Where did the other 6.5 go? Well, remember, you only use 0.059 from the 0.17. The difference is in here. You only used a fraction of that 10, not the whole 10, right? I mean, you could work out what is 0.059 times 58.45, and that'll tell you actually how many grams you used if you want to do that. All right. Now, last one. Little tricky, this one. All right, little tricky, right? This is like a true test skill, right? If you can do this one, you know this, right? Because it's a kind of a trickier question. It's called like odd numbers, right? Okay, so if you want to pause, try it, and then come and look how I did it, all right? Okay, so let's take a look. So 10 of these, 10 of those. Oh, we've got to balance it first, right? So look here, so one aluminum, fair. Oh, I got that whole 3-2 thing, right? So I need 6 chlorine, so that's 2 of those and 3 of those. But then I got 2 aluminums. So it balances up 2 aluminums, 3 Cl2s, 2 AlCl3, okay? Right, now, that's our destination. All right, let's climb down. Let's get the molecular weights. Aluminum, 27 grams per mole, periodic table. Chlorine, 35.45 plus 35.45, 70.9, okay. Here, aluminum chloride, I'm just copying the numbers over from my notes. There we go. So that's what we can fill in, right? So now we've got to climb down, Which one of these is limiting, which one's excess? Climb down, 0.37, 0.14. Now, this is where it gets a little tricky, right? Because these are crooked numbers. These are in a 2 to 3 ratio, right? So the simple question is, well, this one has to be bigger because it's 2 makes 3, right? But how many times bigger is it? It's not twice as much, it's not half as much. What's the ratio of 3 to 2? It's actually 1.5, right? So this one to be perfect has to be 1.5 times bigger. Let me just do that, 0.37 times 1.5. 0.555. So if it's under my finger, 0.555, it's perfect, yeah? It has to be 3 to 2 times bigger, 3 from 2, 1.5 times bigger, 0.555 to be perfect. So if it's bigger than 0.55, it's excess. If it's less than 0.55, it's limiting. It's limiting. The reason that was tricky was because it's a crooked number ratio, right? It's not even numbers, right? Okay, so that one's limiting, that one's excess. Okay, hopefully that makes sense. Now that makes life tricky because we have to slide across with this one because it's limiting, right? Ooh, now that's a problem. How do you turn a 3 into a 2? It's not half as much, it's actually 2/3, right? 2 is 2/3 of 3. So you got to multiply by 2/3. So what is 0.14 times 2 equals divided by 3 equals 0.093. 0.093. So 0.093 is 2/3 of 0.14. Hopefully that makes sense, right? And then it's just multiply to go up, and you should get 12.4. Again, 20 grams doesn't equal 12.4. We used the whole 10 here, but we must have used only 2.4 of that if you think about it, right? From the excess, we only used a small amount. Okay, all right. So hopefully that makes sense. That's limiting reactants. Be comfortable with this, right? So practice ones with excess reagents first. Combustion is a great example for excess reagents, right? Because you don't worry about oxygen running out from the atmosphere. And then when we start throwing stuff in test tubes, you have to figure out, let's just go from the top again. You have to figure out which one is limiting in ratio, which one is limiting in ratio, which one is limiting in ratio, and then slide across again in ratio and get back up. Okay, that last one, if you got it, very good, right? I don't normally ask questions with crooked numbers, but be ready for it, you never know. Okay. All right, hopefully you did this one. I asked you to do this one in the last packet. All right. Let's look here. Now, the answer is there. Okay, the answer is there. Let's kind of talk you through how you would do this one. All right, so I got 6. Well, before I go through it, my advice is, of course, practice exam question, try it. If you got 10, fantastic, right? The answer is 10 grams, right? But if you didn't, maybe hang out and watch, right? So 6 lithiums plus a nitrogen gas, 2 lithium nitrides, right? Grams, molecular weight, and moles. And let's read that old question here. Let's read the question. So 7 grams of each reactant. 7.0 grams. All right. Each reactant. All right, 7.0 grams. All right. Undergo reaction with 85% yield. Now, this will work out a theoretical yield, which is 100%, right? And what you'll do, you take that off on the side and turn it into an 85% of that 100, right? So that's something we do last, right? Okay. So how many grams were obtained at 85% yield when 7 and 7 were mixed, right? So molecular weight. My periodic table is around here somewhere. Of course, I can't find it, so good old Google, right? So lithium, I think it's 6 point something. Molar mass of lithium is 6.941 grams per mole. Nitrogen, 14 plus 14 is 28 grams per mole. And then lithium nitride, so that's going to be, it's quick math here. Let me find my calculator. All right. 6.94 times 3 equals plus 14 equals 34. Okay, so we're following the script. Okay, we've written down what they give us from the question. We've written down the molecular weights just by working them out. We've figured our destination, right? Okay, so our journey is here to here, then a comparison, who's limiting, then we slide, right? So it's going to be close to 1, isn't it? So 7, divide to go down, divided by 6.94 equals, oh, right around 1. That's nice. All right. Now 7 divided by 28, hopefully you can do that in your head, right? 0.25. So I picked some nice numbers. Okay. Now be careful. It's the 6 to 1, right? So I'm going to cover that up. Cover that up. Actually, it's probably better to go this way. If you think, I like to kind of multiply it rather than divide down. That makes sense. So one of these reacts with 6 of these, right? So what's a quarter times 6? 1.5, right? Oh, it's only 1, so that's limiting. Even though it's a bigger number, 1 is bigger than 0.25, it has to be 6 times bigger to be perfect, right? It has to be 1.25, which is 0.25 times 6, right? But it's not that number. It's not 1.5, is it? It's 1, so that's limiting, that's excess. We slide across with that one then, right? Okay, so 6 makes 2. Well, you just 6 into 2 is divide by 3, right? So divide by 3. So 1 divided by 3, 0.33, right? 0.33. Okay. Moles. Multiply to go up. Times 34.82 equals 11.6. Now that's 100% yield, right? Some people on a test would stop there thinking it's all done, but it's not, right? For, what do we want? 85% yield, therefore 11.6 grams times, you can just put times 0.85 to make it a percent, right? 11.6 times 0.85 equals 9.86 grams. Round. I did some rounding up here, so yeah, I mean, if I didn't do the rounding, oh, sorry, move that up. So, got the number. That's the 100% yield, right? Turn it into an 85%. You know, mine's a little off, right? 9.9, so 2 significant figures. I put 10 over here because I didn't kind of, you know, work these out as accurately as I could. But should you have looked at the periodic table, this would be more significant figures, okay? So, hopefully that makes sense. Last one. Oh, okay. I got the answers. Okay, my advice for these guys is molecular formula, empirical formula is actually pretty straightforward. We did the one with the ethylene glycol and we did the aluminum chloride. So it's just kind of a variation on a theme. I think you could probably just do that without my assistance. So we'll kind of stop here. I'll get this one posted. Again, I think I put on the internet, try and get this one done by on the canvas. Try and get this one done by the end of Tuesday. Okay, so try and get this one done by the end of Tuesday, and then we'll go to the next one. Okay, stop there.